So if we recall, essentially, was it 2 weeks ago? Close enough, week and a half ago. We were looking at, the factor theorem and the remainder theorem, and we went through that idea of, P of alpha, whatever it is, if that equals 0, then x minus alpha is a factor. And we could more or less, provided provided something to do with I think it's the coefficients all being integers, we can factorize it just using that. Without, because I think, did we go over, I think we went over the fact that the factors, the integer factors, or the integer zeros, I should say, are all factors of the constant on the end. Have to be whole numbers, yeah. Yeah, so there was that question that we did, and I think, I read in the next section that I think it's to do with the coefficients. So what were all the coefficients in that question, do you remember? Were they all whole numbers? Yeah, so I don't know then, all right. But yeah, something to do with that. But yeah, obviously, if you start going into, if any of the zeros are fractions, there's way too many possible factors if you include fractions. So anyway, here they go through 6 theorems that come away from that, and I'm just going to go through them fairly quickly, I guess. So several distinct zeros. Suppose that several distinct zeros of polynomials have been found, probably using test substitutions into polynomial, whatever it is. Then if you say alpha 1, alpha 2, and alpha s, however many distinct zeros we have, this is the, if you have it in terms of x minus alpha, x minus beta or whatever, or, several numbers of alpha. So like alpha 1, alpha 2, so on and so forth. So those alphas are what it's talking about there. Then, yeah, if you have those distinct zeros of the polynomial, then obviously x minus alpha 1, x minus alpha 2, however many there are for the polynomial, they're all factors. They go through the proof. Because alpha 1 is a 0, then x minus alpha 1 is a factor, obviously, and p of x is equal to x minus alpha, and then the remaining polynomial that comes after that, so p1 of x. Because alpha 2 equals 0, but a2 minus a1 is not equal to 0, in other words, that a2 and a1 are not the same number, so they're distinct. P1 of a2 must also be equal to 0, hence x minus alpha 2 is a factor, and then so on and so forth. You keep doing that continuously until you have all of the factors. It's just the building block of what we've been using, essentially, and something that you can extract from that. So those are several distinct zeros, as opposed to all distinct zeros, which we'll have a look through in a sec. Again, what we go through is a lot of kind of background info that doesn't necessarily come up in the questions, but is useful for establishing the grounding. If n distinct zeros of polynomial degree n can be found, then the factoring is complete. Obviously, you can't have more zeros than the degree of the polynomial. That's how it works. A quadratic has 2 zeros, a cubic has no more than 3 zeros. Same with the quadratic has no more than 2. Cubic no more than 3, quartic no more than 4, so on and so forth. Then obviously if you find n zeros of an n degree polynomial, then you finish factoring. Quartic is to the power of 4, isn't it? Yep. So it can have a maximum of 4 zeros. Yeah, so it is in its normal form, but I believe it can also do this, depending on its shape. But yeah, if it's just x to the 4, rump kind of thing, but a bit flatter on these edges. But variations of it can look like that. Yeah, pretty sure. And hence the 1, 2, 3, 4 things. So by the previous theorem, we have those things that are factors of p of x. So p of x is equal to all those things times some polynomial q of x. That's possible, but p of x and those things, they both have degree n, so that means q of x must be a constant. And that constant could be 1 or anything really. So equating coefficients of x to the n, the constant q of x must be the leading coefficient, meaning it's just the number that's going to obviously be whatever the largest, well, it could be the coefficient of everything, but as in the same number being the coefficient of everything, but it would definitely be the coefficient of, or the leading coefficient, because just by its nature, if it's multiplying with this whole thing, you know, when you eventually expand all the x's, your constant would be multiplying with that. Okay. Factoring polynomials, finding several zeros first. We can find more than one zero of a polynomial, or if we can, then we found a quartic or cubic factor, and the long divisions are required to reduce, can be required to reduce, or even, sorry, and the long divisions required can be reduced or even avoided completely by testing with zeros that are factors of the constant. Okay, so we can use trial and error to find as many integer zeros of p of x as possible, or we can use long division. So the coefficients of p of x are all integers. If the coefficients of p of x are all integers, then any integer 0 of p of x must be one of the divisors of the constant. Were all of our zeros in that question non-integer, or was there one that was an integer? Well, that's a doozy. Okay. There is an explanation for it, but I don't have it yet. Okay, so when this procedure is applied to the polynomial factored in the previous section, rather than 2 long divisions required, you can just, rather than having 2 long divisions, you can do less than that. Okay, so factor this thing completely. P of x equals x to the 4 minus x to the 3. So what are the possible alpha values? When I say alpha values, I mean zeros. What are the possible zeros that could factor this? 4 minus 4, correct, yeah. So it's going to either be x equals 1 or -1 or 2 or -2 or 4 or -4. Yeah, well, we'll start off with 1. So p of 1 equals 1 to the 4 plus 1 to the 3 minus 9 times 1 squared plus 11 times 1 minus 4, which is, what's that? So 2 minus 9 is -7, plus 11 is +4, minus 4 is 0. Okay, it's all good. I do make mistakes. Okay, so therefore, x minus 1 is a factor, great. Well, let's keep going now, because the other ones have to be there as well. So what's p of -1? So -1 to the 4 plus -1 to the 3. Well, those two are going to cancel out. Minus 9 times -1 plus 11 times -1 minus 4. So we get 9 minus 11 plus, minus 4. Minus 4. And that's not a factor because what's that? It's -2, -6. So is a factor. Therefore, x plus 1 is not a factor. And there is another way of writing that, but we'll just leave it like that for now. So p of, we'll go 2 equals, and here's the thing, like, you don't need to write all these out. Once you get the thing in your calculator, you can just be like, oh yeah, p of 1 is 0, p of -1 is -6, so on and so forth. So I'm not going to try and do that. So 2 to the power, you already know? Okay. So is not equal to 0. What about p of -2? 2 to the 2 power Hmm?
Oh, yeah.
Oh, come on. I almost thought of it.
Yeah.
Oh,
P of 4. I'm going to go through and change all these. Actually, I'm going to do negative 4 first because I've got it. Or the negative's already in there. And then P of 4. How's that? Oh, whoops. I made a mistake on this one. That's not 22. But yeah, anyway. And this one's 216. So that's not right. Let me go through and change the negatives again. Negative 4. Negative 4. Negative 4. Negative 4. 0. Okay. Now we've tested them all, and I have a quartic thing here, and I've only found 2 zeros. Well, either that or we have another polynomial on it. So we've got, so x plus 4 is one here. So factors.
do another one.
So we've got x minus 1, x minus 4. Well, I think what we have to do here is we have to do a long division using that as our factor. Hmm?
Yeah, it is X.
Thank you, it is. Yeah. Okay, so we'll do our long division with that, and that ends up being x squared plus 3x minus 4, and long division of that and our x to the 4 plus x to the 3 minus 9x squared plus 11x minus 4. But at least, at the very least, we only have to do one long division, I think. No, we will, yeah, because this, whatever this answer here will be something that doesn't have zeros. Yeah. Okay, yeah, x squared. So maybe there is, but anyway. Plus 3x cubed. There's going to be something that we'll look at possibly tomorrow. That's another way of doing these. Yeah. Minus 4x squared. That minus that is going to be negative 2x cubed. That's going to be negative 5x squared. And that's plus 11x minus 4. So negative 2x, negative 2x cubed, minus 6x squared, and plus 8x. Cool. 0, that's going to be x squared. This is going to be 3x. And that's minus 4, that's fine. And look at that. And that's literally plus 1 on the end to take care of that. So our two factors then, well, essentially all our factors are x minus 1, x plus 4, and very good. It does. So this factors into what? X minus 1 squared. So essentially then we've got x minus 1 cubed, x plus 4. Cool. So the only problem there is, like, you know, you can do these, but you don't necessarily know whether or not it's because it's a 0 of a higher degree, or if it's something that can't be factorized, like if that was minus 1 there. No, it could still be factorized. Could it? No, it couldn't. Anyway, surely it could. Anyway, moving on. I don't think it could. Like, surely it would have to be. It's just, I think it's, I think it could, but it's going to be surd zeros. Yeah, it's not fun. Because if it can be factors there, then it's below the line, and so moving further down, it would still be below the line. But yeah. Okay. So the methods of the next section allow this particular factoring to be done with no long divisions. This example involves a polynomial that factors into distinct linear factors, so that nothing more than the factor theorem is required to complete the task. So we'll try that. So at least we don't have to do a long division. What are the factors of 6?
1.
There's a few. So yeah, 1, -1, oops, -1, maybe. Yeah, 2, -2, 3, -3, 6, -6. Okay. But as soon as we get to 4 of them, we're done. Okay. Now it does have to be a combination of things that multiply to give us 6. So let's keep that in mind as well. So it could be, you know, 1 and 1 and 2 and 3. Could be that anyway. Or it could be, well, actually it can only be 2 and 3, like in terms of if you think about things multiplying to give you 6. 2 and 3 can only happen once, and I think they actually have to happen once, because 2 and 3, otherwise, unless it's 1 and 6 with like a whole bunch of 1s, like 1 to the power of 3 and a 6. There's only so many combinations, and I think we can pretty much figure out what the combinations are from that. All right. So P of 1 gives us what? Thank you. P of 2? Oh, P of -1?
Also 0.
Yep.
Yep.
0. Okay, good.
P of 2 is not, and P of -2 is not. P of,
yeah, so 2 of them have been taken up by that now. So technically, and it's not 2, therefore it must be 6. Can we see why it must be 6? So if 2 doesn't work, well, 3 can't work, because no combination of 1, 3, and 6 will give us 6. So, so 1 and -1 work. So then we've got P, oh, not P, sorry. Essentially, this implies we've got X, -6 will have to work, yeah. So X minus 1, X plus 1, and then X something to do with 6. Has to be. Oh, wait, no, it doesn't. It'd have to be -6. No, +6 would work, because alpha is, like, remember it's X minus alpha. No, but like if he plugs in -6, that would be X plus alpha. Like X, if he's plugging in, remember it's the opposite. Yeah. You got -1 times 1 gives you -1 times -6 gives us +6.
Yeah. In the when I factorize it, the bracket's going to be X plus 6 because my intercept is 6. Is -6. What? Like you know,
You're talking about Y-intercept?
Sorry?
You're talking about a Y-intercept? If you're looking at your X-intercepts, then yeah, this is at X equals 6, like 6 here, -1 and 1. But I'm not really concerned about that. What I'm looking at are my factors in terms of X minus alpha. remember if x minus alpha, then p of alpha equals 0 implies factor. And so, like, all I'm doing right now is multiplying that, and that needs to result in positive 6. So if we've definitely got a negative 1, which we do, and we've definitely got a, unless the alternative is if this is squared, this can be positive.
Yeah, negative 2 works.
Negative 2 works.
You said it didn't work.
Josh, you said it didn't work.
Right?
No. So negative 2 does work.
Yeah.
Okay, so we've got x minus 1, x minus 1. So that means one of the 3's have to work. Okay, so x plus 2 works. Not my fault.
3 works.
At least I have chicken. Huh?
3 works.
3 works, of course it does. So as in when you plug in positive 3 it works?
Yeah.
So x minus 3. I'm sorry? No.
Oh, sorry.
Yeah, it wouldn't. No, it's taken up with those two things.
That's true.
That's okay. Yeah. So we got x minus 1, x plus, and so what was that? So p of 3 equals 0. So we have our factors. So we factorized it there without having to do a long division. I mean, honestly, provided you plug your numbers in your calculator correctly, then, you know, it's going to work. Yeah. All good? Okay. Jen's not amused. That's okay. I know sometimes I'm like, oh, gives me, if looks could kill, I would have been dead much earlier in the term. What are you doing? Okay. The maximum number of zeros, this is very logical. So if a polynomial of degree n were to have n plus 1 zeros, then by the first theorem above, it would be divisible by a polynomial of degree n plus 1, which is impossible. You can't divide a polynomial by a polynomial of a higher degree than it. There's a lot of stating the obvious, but it needs to be stated because not everyone sees the obvious. That's more or less. There's better reasons than that. Ooh, finish charging. But yeah, that's part of it. Like theorems, a lot of them are, yeah, that. And sometimes proving the blatantly obvious is quite difficult. So can't think of an example right now, which is in and of itself is an example about how proving the blatantly obvious isn't always easy. I actually don't have the I don't know the proof for it. There is a proof for it, essentially. it's to do with things. Okay. D, a vanishing condition. So the previous theorem translates easily into a condition for polynomials to be a zero polynomial. Shh. Suppose p of x is a polynomial in which no term has a degree more than n, yet is 0 for at least n plus 1 distinct values of x. Then p of x must be the zero polynomial. In particular, the only polynomial that is 0 for all values of x is the zero polynomial. Otherwise, it would have other values. Yeah, they have a proof. I'm not going to go through it. Fine. Suppose that p of x has a degree. This degree must be at most n because there is no term of degree more than n, obviously. But the degree must also be at least n plus 1 because there are n plus 1 distinct zeros. This is a contradiction, so p of x has no degree, therefore the zero polynomial. Yeah, I'm sure you do. Once again, yeah, so that's the z polynomial, the zero polynomial is there, and blah blah blah, it goes on. Okay, condition for two polynomials being identically equal. A most important consequence of the last theorem, is my laptop's got coronavirus now. Is a condition for two polynomials, p of x and q of x, be identically equal, meaning that obviously p of x is equal to q of x for all values of x. So every value of x would be the same when you plug them in, the y value. Okay. So suppose p of x and q of x are degree n polynomials that have the same values for at least n plus 1 values of x. the polynomials p of x and q of x must be identically equal. That is, they're equal for all values. The result was foreshadowed in box 4 of section 10a. But anyway, I'm just going to continue on. Proof. They have the proof of it. Who cares? Here we go. So find A, B, C, and D if we have this thing here and we don't know essentially our constants A, B, and C, and D for at least 4 values of x. We can do this though. Now, if I know that x to the power of 3 minus x is equal to A outside of x minus 2 to the power of 3 plus b of x minus 2 to the power of 2 plus c of x minus 2 plus d. What's something that I can immediately tell about one of these values? What's going to be 2? No, not the zeros. Just the A, B, C, and D's. A, B, C, and D. I just can't remember going through this proof.
Wow.
Yeah, but there's an immediately obvious one that you can take the. Oh, that's right. Yeah, obviously. Okay. It is. If we sub in x equals 1 into the left side, what do we get?
0.
What about x equals? Oh, actually, we can continue. Well, the easiest one. I mean, obviously, x equals 1. Yeah, 0 on the left side. On the right side, it's going to be something. X equals 2. We're going to get, yeah. So essentially, here it'll be 8 minus 2 equals. Well, that goes to 0. That goes to 0. That goes to 0, and I get left with d equals d. So I can say 6 equals d. Great, I've got my first term. Fantastic. And then we'll do x equals 0 and sub that in, because then obviously 0, x equals 0, x equals 2. 0 then equals alpha outside of, what's that, negative 8? Negative 8, alpha, not alpha, sorry, a. Plus 4b. Was it a c? Minus 2c plus 6. Cool. Can divide everything by 2 for starters. So 0 equals negative 4a plus 2b minus c plus 3. And so where do we go from here? I think I just want it like something in terms of the other one. What did they do? What they got? It's supposed to be A. Where'd the alpha go? Well, not alpha, sorry. Where'd A go? That's my question. Oh, of course. Okay. Yeah. Yeah, that's a good point. So we can essentially eliminate this one. Why can we eliminate this one? If I'm equating the coefficients of this and this, my coefficient of x cubed is 1, which means the result out of here, A must also be equal to 1. Oops. C. Yeah, C should also be equal to negative 1. Oh, no, it's not. No. Yeah, good question. I don't know. I'd probably have to watch the video. Well, I guess by that logic, the coefficient of well, B would have to be 0 if we're completely equating coefficients. I think it's to do with the leading term. you can only do it with the leading term. That's what's making sense to me at the moment. Yeah. Because otherwise, yeah, B would have to be 0, B would have to be 0, but not, D is 6. So it's like, because when you expand all these things then and collect like terms, then they'd be different things. Okay, well, let's move that over. That wasn't negative. Start that one again. So if x equals 0, we get 0 equals, that term is just 1. And so it would be, so negative 8, just on its own, plus 4b, and what was it, minus 2c plus 6. So we get 0, or rather 2, I'm sorry? So we can equate coefficients of the leading term, but we can't seem to equate coefficients of any of the following terms. I guess it's because once these expand, some different things could happen. The other thing is there's going to be, for b here, if I expanded this, I'm sure I'm going to get an x squared, but I'm also going to get some x terms, like, plus or minus. In fact, that is why, yeah. Guys, the reason we can't equate coefficients on anything except the leading term is because all of the previous terms affect the other terms. So the only term that isn't affected by the subsequent terms is the leading coefficient. We good with that, Josh? Daniel? Why? You literally weren't listening to everything I just said then. So the reason we can equate coefficients with this one and this, but not anything else, is because when these things expand, they affect how many x terms there are. Because this term has, sure, an x cubed term, but it also has an x squared term and it has an x term, and however, like whatever they are as well. So the only one that remains unaffected is the leading coefficient term. Are you okay with that? Does that make sense? No? Yes? Okay. If I expand this, I've got x squared minus 4x plus 4. If I expanded that, yeah? That's going to have an impact on this third term, this c, which is, x minus 2. Well, I've got negative 4x and I've got an x there. They come together, that's negative 3x, but it's also going to be affected by the first one and whatever the x values are in there, plusing and minusing. It's not going to be whatever number this is, or it could be, but it's likely not going to be that. I can't say for a fact it is. Whereas with the first term I can, because x cubed, there's no other x cubes. There's only one x cubed. So a has to multiply with that, therefore they must be the same coefficient. Yeah? Yeah, okay. Okay, so then that's 2. So 2 equals 4b minus 2c, therefore obviously 1 equals 2b minus c. And what have they done there? Oh, that's it. Okay, we've got that. We've got 1 equals 2b minus c. And then lastly, they substitute in x equals 1, which also works because 1 minus 1 is going to be 0. So x equals 1 implies that 0 equals, can someone do these for me? 1. So obviously we've got 1 outside of, now 1 minus 2 is negative 1 to the power of 3, which is negative 1, good. Plus negative 1 squared is positive 1, so b, and then minus c plus 6, which is 5 plus b minus c. So c equals 5 plus b, and we've essentially got 1, 2, 3, and a sub 3 into 2. I think that's what we do, yeah. Which means that I get 1 equals 2b minus 5 minus b, which is equal to b minus 5, and so 6 equals b. So we've got a equals 1, b equals 6, c equals clearly 11, and d equals 6. Okay with that? Mostly?
Yeah.
Yeah, that's a good thing to remember. In fact, I want to write that in. The leading term coefficient can be, what's it called when the equator can be equated on both sides, but the other terms cannot because they don't correctly indicate same thing on both sides. Think expanding. Cool. That works for me. I should put a note in there anyway. F, G, and then where are we going? We're going to have to stop at some point soon. Let's see how we go. Identically equal polynomials. So obviously the questions that you're going to get are going to be something along the lines of those. Factorizing without doing long division, with doing long division, and then trying to find these coefficients and stuff. If two polynomials p of x and q of x are identically equal, then p of x is equal to q of x or value of x's. Yes, that's fine. We're okay with that. Geometrical implications of the factor theorem. So the graph of a polynomial function of degree n is completely determined by any n plus 1 points on the curve. The graph of two distinct polynomial functions can't intersect in more points than the maximum of the 2 degrees. Makes sense. If they are combined together, they would have no more degrees than what they already have. If they're multiplied, then obviously there would be more. That's fine. A line cannot intersect a graph of a polynomial of degree n more than n points. So if it was squared, then a straight line could only intersect it in 2 places at most. If it was a cubic, 3 places at most. Chordic, 4 places at most. Yeah. In parts 2 and 3, points where 2 curves are tangent to each other are to be counted according to their multiplicity. Cool. That's okay. I think I copied the actual solution in here because it was like I wasn't too worried about it. So by factoring the difference, so if f of x is equal to p of x minus q of x, describe the intersections between the curves. So you have p of x and q of x, they're both the same degree and very similar functions, or not really similar functions, I guess. This one doesn't have an x squared term, this one, neither does this one, but this one doesn't have an x term, and this one does, and there's no constant. This one is. Firstly, where does this cross the y-axis? The origin, because there's no constant term on there. Dun, dun, dun. So we can actually do the subtraction there, and if you minus 1 from the other, obviously that's a polynomial of degree 4, but you've got 2 polynomials of degree 4 subtracting from each other, which can result in a polynomial of either degree 4 or less, because the x to the 4 terms can disappear, and in this case they did. We've got f of x, so it's x cubed minus 3x plus 2. If we sub in, if we try and find f of 1, we get 0, so that's a factor, and f of negative 2 is also a 0, so that's a factor too. And then they do a long division, and we get f of x equals x minus 1 squared, x plus 2. Now remember, with the degrees thing, let's just have a look at this and think about what does this part look like. Like what's the nature of the curve like here? Yeah, it's happy face. It's happy face. It's a turning point. It's a turning point. Remember, it's touching the x-axis but not going through it. Yeah. And then this one, sorry. Well, because it's a turning point and that's a 0. So essentially you've got 2 zeros happening there, but that's 1 0. And then this one just passes through with no special characteristics. Remember, if it's a degree of 1, it passes through, nothing special. Degree of 2, it touches and doesn't pass through. degree of 3 passes through point of inflection at the origin, and then from there on, if it's even, it touches, if it's odd, it's a point of inflection. So the only one that is odd and not a point of inflection is degree 1. Cool. So hence y equals p of x and y equals q of x are tangents at x equals 1, but don't cross there, as it says. And there's an intersectional. Oh, right. So when we're looking at the zeros of this function, this tells us characteristics of the intersections between the other two functions. So this is saying that if we plotted p of x and q of x, p of x and q of x would touch each other at this point, but they wouldn't cross over, and then they would cross over at this point. Yeah, and if you plot that in GeoGebra, you'd see the result with that as well. It looks pretty funky, but they touch here at that point, but then they don't cross over, and they do cross over here. So that's it. Like, it's the combination of the two tells us something about each one and where they intersect with each other. Hence, p of x and q of x, they're a tangent but don't cross. They intersect at x equals -2, where they cross at an angle. Because f of x is positive for x is between -1 and 1, or x is greater than 1 and negative x is less than 2, then p of x is above q of x for those same sections. So that's kind of how you can look at that as well. Like we've gone p of x minus q of x, p of x minus q of x, and so whatever in the combination of the two, when we've plotted the new function, wherever it was above the x-axis represents where p of x was above q of x, and wherever it was below the x-axis represents where p of x was less than q of x. And thus, you would be able to plot these two graphs knowing where they intersect and where one is greater than or less than the other one. Maybe. I think you might need some more information than that. A note for extension 2 students. Anyone wanting to do extension 2? Maybe? We'll see. So the fundamental theorem of algebra cannot be proved in the extension 2 course because it goes beyond the scope. But the theorem helps understand the importance of complex numbers for polynomials. It tells us that every polynomial of equation degree n has exactly n roots. And some of those roots are, here we go. So provided first that the roots are counted according to their multiplicity, and secondly that complex roots are also counted. So even where it doesn't cross the x-axis, but you're still counting it as an imaginary root. So because x to the power of 3 has one root of x equals 0, but this root has a multiplicity of 3. So hence, anyway, x to the power of 3 minus 1 equals 0, which has factors of that, and has a root of x equals 1, but also has two complex roots from that one there. And so ultimately, this means that the graph of polynomial of degree n intersects every line in exactly n points, provided that the first points where the line is a tangent are counted according to their multiplicity, and secondly, that complex points of intersection are also counted. I'm going to stop there because who cares? But before we go on, what I do want you guys to memorize for tomorrow's class, and it just makes it heaps easier. Okay. Alpha plus beta equals -b on A. Yep. Alpha times beta equals C on A. Okay. Alpha plus beta plus gamma equals -b on A. That's good to know. These two are the same. And then then we have alpha beta plus plus what doesn't really matter. Beta gamma plus alpha gamma equals C on A. And then alpha beta gamma equals -d on A. Yeah. They are given to you. They do provide those in exam situation, but it makes it easier to remember some of these things. That's what we're doing tomorrow. Stuff to do with that.
I don't know any of those.
These are roots. These are roots.
Oh, okay.
Right?
Is this only with x to the power of 3?
So there is n polynomials for an nth degree polynomial as well. But essentially, this is what we have to do. And that will be tomorrow's class, which is a bit better. And I forgot to stop the recording, so that was all on there as well.